Welcome to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In this video, we will be looking at Cape Chemistry, Unit 2, Module 1 for 2024. Let's go. For the first question in Module 1, the chemistry of carbon compounds, let's start by examining the question. So a hydrocarbon compound whose molecular formula is C8H18 was determined to have a given number of isomers. The first thing we must do is to define the term structural isomers. So a simple definition is that structural isomerism is the existence of compounds with the same molecular formula but different structural formulae. For A part 2, you are required to list 3 types of structural isomerism. The 3 types of structural isomerism are 1. Chain isomers, 2. Positional isomers, 3. Functional group isomers. A part 3. Define one of these types of structural isomerism listed in A part 2. So pretty much we are to define any one of these. So let's start with chain. Chain isomerism is shown when isomers have different carbon chains, that is, different arrangement of carbon atoms. For positional isomers, this occurs when the isomers have different position of the functional group in each isomer. And for functional group isomers, this occurs when the isomers have different functional group and therefore different homologous series. So if you're looking at functional group, you can move between an aldehyde and a ketone. You can move between esters and carboxylic acid, and between alcohol and ether. Let's continue. 1 part B. Draw 2 isomers that have 1 methyl substituent. So we are still looking at the molecular formula C8H18. So if we were to look at the question, you can draw 2 isomers, but you must have 1 methyl substituent. So we can start with 7 carbon in our parent, and our methyl substituent will be the 8 carbon. Remember that isomers must have the same molecular formula but different structural formulae. So in the first one with 7, 1, 2, 3, 4, 5, 6, 7, that's my parent, and the methyl group is the branch group. So this makes our 8 carbon. And of course we have 18 hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. In our next isomer, we simply move the methyl group from the second carbon to the third carbon. So in the first isomer, we have 2 methyl heptane. And in the second one, we have 3 methyl heptane. Another one could be 4 methyl heptane. And once you do that with your methyl substituent, you satisfy the question. B part 2. Draw 3 isomers that contain only secondary and tertiary carbon atoms and at least 2 methyl substituents. So this time, we are looking again at the same molecular formula, C8H18. So if we are to draw secondary and tertiary carbon with at least 2 methyl substituent, we can't start with 7, and we can't use a straight chain with our parent having 8 carbon atoms. So we will move down to 6. So that's 1, 2, 3, 4, 5, 6. And then I have 2 methyl substituents. Now these methyl substituents are groups that substituted H atoms from the parent. So in the first one, we have on the second carbon, we have 2 methyl branches. And again, our parent would contain 6. So that would be hexane. So this would be 2,2-dimethyl hexane. Now, it is tertiary because we have this carbon attached to this carbon. And the carbon that is attached to is linked to 3 other carbons. So here we have 1, 2, 3 carbons. So this carbon is your tertiary carbon because it is attached to 3 other groups coming off the branch methyl group. In the other molecule, we simply move one of the branch from the second carbon to the third carbon. So this becomes 2,3-dimethyl hexane. And this now is a secondary group. So our methyl group is attached to this carbon, but this carbon is attached to 2 other carbons, hence secondary. We could move to draw another one where we move the branch methyl groups to the third carbon, making it 3,3-dimethyl, and the parent is hexane. And this would be a tertiary carbon atom because this carbon is the branch methyl group attached to a carbon that's attached to 3 other carbons. That's 1, that's 2, that's 3. Hence, this isomer is a tertiary hydrocarbon. We can draw another one where we move one of the methyl group from the third carbon to the fourth carbon. So we'll have 1, 2, 3, or 1, 2, 3. And if this is our third carbon, then this becomes our fourth carbon. So it would be 3,4-dimethyl, and the parent is hexane. And we could continue like that to move the methyl group to different carbon and name it. So that basically gives you your 3 isomers. And again, you can draw any 3 of these would be correct. So you draw any 3 of these isomers, and you have only secondary and tertiary carbon atoms present. And of course, we have at least 2 methyl substituents in our diagrams. Let's continue. 1 part C. The scheme in figure 1 shows a sequence of reactions that indicate the outcome of the reacting of an isomer of hydrocarbon A. Carefully examine the scheme and answer the questions that follow. All right, so we're looking at this scheme going from A to B to our structure at C. So let's see what does that mean here. If you look at this particular structure, you'll see that we have 2 OH group, 2 hydroxyl group. So this pretty much is a diol, and this is a skeletal structure. So if you look at the skeletal structure, you can see that it is coming from a hydrocarbon. So A is our hydrocarbon. Now, how do we know that A is our hydrocarbon? Because A is reacting with chlorine and UV light. So this part is free radical substitution. Now, if it is free radical substitution, we must have a alkane, and in this case, this is our alkane structure. How do we know? Because if you look at this skeletal group, we have 1, 2, 3, 4, 5 carbons. So we can start like this. So we say 1, 2, 3, 4, 5 carbons. And this is a branch at the top. So that's our CH3. And this OH I'll put right here. And this, of course, is CH3. So this is our first CH3. This is our second carbon with a CH3 branch, a methyl branch, and a OH branch. We then move to the third carbon, which gives us a CH3 group. And this is a H group, then a CH3 group there, and a OH group there, and of course, the last CH3 group. So this is our structure, C. Now, if we're coming from A is a hydrocarbon, and it is an alkane. Now, if you react it with the chlorine and the UV light, it is free radical substitution. So pretty much, we're going to substitute our Cl where these H's are present based on our molecule at C, or our structure at C. So these 2 H's will be substituted by chlorine atoms. So at B, I would have my halogenoalkane where I have my Cl replacing my H's. And of course, going to our structure C, we need a reagent that is going to now hydrolyze and remove the Cl and replace them with OH to form our diol. So compound A is pretty much your alkane. And this is what we draw for our alkane, which I showed you here. So this is the displayed structure showing you our H's that will be substituted for part B. So for part B, to go from my halogenoalkane, I'm going to go through hydrolysis. And the mechanism that will take us from that structure to the dial is nucleophilic substitution. And in this case, it is going to be SN1. Because of the tertiary carbon here, it cannot be SN2. So because at B, we form our halogen alkane, and we have our reagent, which is sodium hydroxide, aqueous sodium hydroxide or aqueous potassium hydroxide, we are going to substitute our Cl with OH groups. So this Cl and this Cl will be removed, and this mechanism will be nucleophilic substitution or unimolecular nucleophilic substitution. So C part 2, you're required to list the names of the steps involved in going from A to B in figure 1. Again, remember that A was our alkane, B would be our halogen alkane, and of course, our structure C would be our dial. But this question is asking us to name the steps involved in going from A to B. So in going from A to B, remember that we said the process or the mechanism would be free radical substitution. And the steps involved are initiation, chain propagation, and termination. See part 3. Using curved arrows, give the mechanism for the first step listed in C part 2 on page 6. So here, we're looking for the first part, which was initiation. So the UV light was used to break the bonds between the chlorine molecules. So we use fish hook notation to show that we are only removing one electron to this chlorine atom and the other electron to this chlorine atom, forming our chlorine free radicals. Part 4. Give the structural formula of a product that can be formed alternatively to the compound B in C part 1. If you recall, our compound B, where our halogen alkane add Cl at this carbon, the second carbon, and the fourth carbon. So that's 1, 2, 3, 4. So the second carbon and the fourth carbon. Alternatively, you could substitute the other H's. So I could substitute a H from this CH3 to form CH2Cl. And then I could substitute a H from this CH3 to form CH2Cl. Again, we could use this H present here to substitute the Cl, and this CH3 to substitute one of the H's. So I have Cl here and CH2Cl here. Another carbon that could be substituted would be these methyl groups at the top, where I could just remove one of the H's, and now I have CH2Cl, CH2Cl. So any one of these could be used as your alternate compound to compound B. So C part 5. Given that ethanol has a pKa of 16, suggests whether the pKa of compound C is higher or lower than that of ethanol. Give a reason for your suggestion. All right, so we're looking at ethanol, and here we have an alkyl group, CH3CH2, which are positive inductive group, so they push electrons towards the OH. Here we have our dial now for compound C. So here we have now our groups, and we have methyl groups that again are positive inductive groups. So these groups push electrons towards the OH. So in explaining the answer, we must understand the meaning of pKa. So pKa is really a measure of the acid strength. So the lower the pKa, the stronger the acid. The pKa of compound C would be higher than ethanol due to the positive inductive effect of the methyl groups, making it harder to release the H plus ions. So if the H plus ions are being attracted by the electrons that are being pushed towards it, then the ethanol would release the H plus much more readily than this compound C. And of course, that would make compound C have a higher pKa value, suggesting that it is a weaker acid than ethanol. Part 6. If the reaction of going from A to B was performed in a closed vessel, what would be the expected color change? All right, so looking at A would be our alkane. You remember A is our alkane. And as it is reacting and going to form B, you'll have a color change from yellow-green as the chlorine is reacting with A to form your halogen alkane. So as you form the halogen alkane, you're going from a yellow-green color to colorless. So remember, A is our alkane and B would be our halogen alkane. Part 7. In an experiment, 2 drops of universal indicator were added to 1 cm cube of ethanol in test tube 1 and 1 cm cube of compound C in test tube 2. Suggest the colors expected in test tubes 1 and 2. This question is suggesting that the OH here is behaving as a base because the universal indicator is used to test between acids and bases. But remember that this hydroxyl group here is representing an alcohol, and these are diols. Now we use aqueous sodium hydroxide, so the OH in the aqueous sodium hydroxide is acting as a nucleophile, not as a base. The only way it acts as a base is if we use sodium hydroxide in ethanol instead of water. Now that would make the OH in the sodium hydroxide behave as a base and not as a nucleophile. So this question should have been different, but for the sake of answering the question, we'll just treat it like they're asking for the OH in terms of the base. So the universal indicator is used to test between acids and bases. So in test tube 1, we have ethanol, which is going to be slightly acidic, close to being neutral. Slightly acidic, close to being neutral. So that would give us a green or blue-green or light blue color. And in test tube 2, where we have compound C, suggesting that we have the OH group and they're thinking maybe of the OH group as bases, then we'd go from a blue-green or light blue in test tube 1 to a blue color in test tube 2, suggesting that it is basic. That would be the most appropriate answer. This is the end of this section from Module 1, Unit 2 Chemistry, 2024. Remember to like, subscribe, and ring the notification bell so that when new videos are uploaded, you will be notified. Thank you.